computer. Okay, so we'll have our Zoom proctored exam on Thursday, normal class time. Need to have your secondary device up and running and ready. So the first thing I want to draw your attention to is in the mass spec, okay? So one of the things that people seem to get points off on the mass spec is that you need to use the exact mass formulas if you're doing the calculation here that are on the table. For example, carbon is 12.0000, not 12.0011, because that 12.0011 accounts for the two isomers, the carbon 13 and the carbon 12. So it turns out carbon 12, the pure isomer, is 12.0000. So just make sure you're using the ones on Appendix A if you're asked to calculate exact mass. Okay. And again, the other thing to do here is if you're given the exact mass of something, then you can actually go down this table and get the empirical formula immediately. You don't have to back calculate it using the rule of 13. Okay. All right. So that is something I want to draw your attention to. Again, in your Appendix B, this is the fragment ions UC. So this is what you should actually have the numbers on the mass spec for. But Appendix C is the fragments that are lost. So that's the difference between peaks. So I actually ended up having to use the difference between peaks to actually solve one of the homework problems because it didn't make sense until I actually used the Appendix C for that. So I wanted to make sure that you drew your attention to that. And don't forget to use that, especially when you're looking at the difference between two different peaks. Okay. So other than that with mass spec, the other thing to make sure that you have, and we actually had that happen, the homework assignment here, is that you actually had things that were done with your regular electron impact ionization, and then you had things that were chemically ionized. Now, when things are chemically ionized, they can have a higher or lower molecular weight, and their fragmentation pattern is different. So it tends to be when you have the chemical ionization, you actually get the full parent ion without losing anything first. So you might have seen that in your homework because there was one example, at least, it had the electron impact ionization and a chemical ionization, and they had two different masses. So make sure you remember how to use those two different techniques and how they have two different masses and what that means. IR spectroscopy, there's nothing really I have there. I think all of our zones are pretty much, what we can determine from that is pretty good right there. I don't have anything to add to that. With the Proton Nmr, I want to draw your attention to a few of the tables that I think are really important. So table 1A specifically is really great when you're looking for the CH3, CH2, or CH that's like at the end of a chain, okay? Because it's really great to tell you that. Or it's in the middle of an aliphatic chain and you have a functional group. So for example, if you had a CH2 that only had a carbon chain on the other side but had like a phenol on it, you would be able to use this chart very well. And remember that the dashed line is 3 hydrogens, the dots, open dots are 2 hydrogens, and the closed dots are 1 hydrogen. But then the complementary one to that is the shift 2 things over, which is the 2A, okay? Notice that's the methylene that is 2 over from the functional group. And so when you use that, you can actually say, okay, so if I use table A for the one directly bonded to it, I can use table 2A for the ones that are bonded 1 over from that and get a pretty good starting place. Now, if it still doesn't make sense or it's shifted a little bit off, then you have to go to Appendix B and actually do your calculation where you start with your 0.23 ppm and then you add the different groups to it, the ones that are attached directly to it. One thing I found very interesting about that is that, it has like all your halogens here and your shifts. And so if you see something shifted all the way to 4, start looking for something that already shifts it up 2 or 3%. I mean, 2 or 3 ppm, so that, you'll be able to start getting a really good prediction on it. Sorry, your whole screen's moving back and forth, Emma. So had to laugh, sorry. And then, and so that kind of falls through to the back half of the page, including the things about rings. In the homework assignment, we had rings. And so there's a couple different ways to do rings. One is to do the calculation in this B2C, which is on page 192 in my book. And it gives you an idea of where they might be and what they might be shifted toward. Although it tends to give you more of a whether or not it's identical or not. But then in section C, this works really well until you have a substitution. So you can get like half of a ring done, and then if there's substitution, you have to start using your appendix B to figure out where shifts are. But it gives you a nice thing of where the different parts of rings are, and that kind of showed up in the homework as well. Appendix D works really well if you have different groups attached to your alkenes. You have your cis, your geminal, and your trans additions to that shift in alkene. That tells you the shift, not necessarily the splitting. But if their shifts are different, that means they're not magnetically equivalent and they're going to split each other. And then that can give you a good idea of where that's going to be. So those are shifts constants right there, not the coupling constants. That's in a different table. And then of course, D2 gives you a kind of a good idea of where some common things would be, including some of the fused rings. I think that's actually something that kind of gets on there. And then of course, D1 gives you mono substituted benzene ring shifts. And what it also does is it has these little things saying ortho, meta, para, O, M, and P on this table right here. That's showing you where they would be shifted differently. So for example, in the case of having an alkyne on your benzene ring, it has an O, comma, and then bracket MP, okay? That means the O is the furthest upfield and the metapara are the other point, which they don't shift, they shift exactly the same. And that's why there's only two things on that table, and why they're in that order. Because you'll notice some of these other ones shift differently. For example, when you have fluorine on there, it has meta, para, ortho. So it's in a different order. That means the meta is most upfield, the para is in the middle, and the ortho is most downfield. So that's how to use that table. I don't think I actually talked about that in particular, but it really becomes useful, especially when you have things like carboxylic acids. There's dramatic shifts in the carboxylic acids if you go all the way down. The ortho, para, and meta are shifted significantly different from each other. And so you can see this, okay? And then again, the proton appendix E, where alcohols show up. It shifts around quite a bit. You try to look for your solvent and see where it is, okay? And then the coupling constants, that only comes into play when you're actually doing those, but I also want to make sure that you are calculating your coupling constant correctly, which is why I gave you the homework with a calculation of the coupling constants. And as a hint, there are 3 different coupling constants on the homework problem, so you should have a J1, a J2, and a J3. Okay. So those are the things I wanted to draw your attention to and either tab them or get familiar with them before the exam. And then after that, I think that you will, really have a good handle on where to go as a reference and what to use, okay? So any questions about those different tables and how to use them? Yes? 2 different mass specs really confused me on the homework. Okay, I can do that. Are you saying something? My computer's been weird about hearing people talk during Zoom meetings. So you might want to type it in the chat room. Okay. I don't know, when I only have 1 or 2 people, I seem to be able to hear fine, but when I have that gallery mode on, it seems to really, really go crazy. Okay. So let me go back to that two different things that we have. We have on the molecular ion peak for things with the chemical ionization versus the electron impact, right? So we had two different ways of doing this. And in electron impact, we get that charged molecular ion species unless it's something that like loses water very readily or it has a very facile leaving group. So it'll like water occasionally it'll leave early. Sometimes it'll you'll never have that full mass peak because it's just such a harsh technique. However, in the chemical ionization peak, in chemical ionization, you typically get an M+1. Now, an M+1 means that you usually use something like butylene or methane. And what that does is that can add a hydrogen to your thing to give it the charge. And then the entire molecule, because it's a much softer ionizing technique, can come through the mass spec. But occasionally you also get like an M+18, okay? And that's the entire methane, okay? Actually, it's an entire water. You'll get either 18, yeah, 18, it should have been 16 or 18, 16. Yeah. It's CH3 plus 2 hydrogens, yeah. So it's a methane. So you'll see that in the chemical ionization peak. And so if you look at, for example, spectrum, I believe I in the homework, right here, we see two different things for, is it I? Yes, it's I. In I here, if you look at our electron impact right here, our molecular ion peak is very small at 90, okay? So, and then we have a little fragmentation at 72 and then a big fragment at 43, okay? That's all we see. But when we do it with chemical ionization, our parent ion peak is now 130, okay? Now, what does that mean? That means that, okay, 90 is probably not our parent ion peak, but somewhere between 119 and 130 might be our parent ion peak, and we just lost something to get to that 90. So if we do the difference between that, and notice that on the chemical ionization peak, 90 is the next biggest peak. So if we start looking at what's lost between 90 and 130 and 90 and 119, that might give us what is lost before we see that 90 peak. Okay, so in the case of I in particular, let's see. Okay, what we're seeing probably is some group that's fairly large, somewhere between, you know, the difference between 90 and 119 or 90 and 130 falls off immediately during chemical ionization. But because we did that, the methane of the, I'm sorry, in the electron impact, but because we did the methane in the chemical ionization, it was much softer, and that group that fell off immediately, like, and I don't know, maybe it's 45 or 47 or 48 weight, that huge fragment falls off before we can ever see it in the other way. So what that's indicating to us is there's some big fragment that falls off really, really easily on that compound there. So that should give you an idea. And if you look back at the chemical ionization, you'll see things that typically fall off like that are water, OH, some of the really fluffy halogens like iodine. And so you'll see those kind of big, good, safe leaving groups, you know, nice stable ions leave. And an example of that is if we look at the fragments lost table and the difference between the chemical ionization and the other one, you'll see, you know, big, huge fragments that fall off easily are like CH3S radicals, one of the ones that falls off pretty easily. Then we also have things like CF3s fall off really easily. And where's that one? The CF3 falls off, and that's a 69 fragment. Iodine falls off, it's a 127 fragment. And Where's that last one I was thinking of? Oh, and 46 fragment, which is a nitro group. Those are really common things to fall off. So anyway, okay. So that's the difference between electron impact and the chemical ionization. And so if you get a decent parent ion peak with electron impact, we don't include the chemical ionization because you don't need it. Okay? Good question. Again, I wanted to, we didn't do that extensively as, you know, compare and contrast when we did it the first chapter, but now we can do it because we have these more complex structures and it allows us to do that. Okay. So I am open for any questions as long as it's not directly related to the, well, as long as it's not an actual homework question that can be related to the homework. So let me try doing that. Maybe I take my bandwidth down by changing my picture. See if I can hear people talk. I guess that's not it. I'm trying to close a bunch of things on my desktop so that, okay. Homework due tonight. I can't figure out from the email, etc. last night. It is, I believe, due tonight because I didn't actually put a due place on the, so now there is a place to actually turn it in on Canvas. So I think I can hear somebody.
I'll try my audio.
Okay, I can hear you.
Can you hear me?
Yes.
Okay. I actually didn't follow right here when you were talking about I in 3.4. I just I was looking at page 168, I guess, and y'all were talking numbers that didn't match up with the thing, so I was a little confused.
That's the NMR. So
right.
In chapter 3, the homework is you can compare the mass spec from chapter 1, the IR from chapter 2, and the NMR from chapter 3. The all chapters are the same.
Got
so and you know, so that means that when we looked at the two mass spec in chapter 1, one of them was electron impact, which is one thing, and then the other one was the chemical ionization with methane. Okay, so we're expecting to see an M plus, you know, methane peak, which is 16. We're expecting to see an M plus 16 peak for that.
Okay.
Or at least a parent ion peak +1.
Right. Okay. Okay. So it does match up with the same relative or relatable scans from chapter 1 and 2. That was my confusion.
In chapter 1, chapter 2, and chapter 3, all are the same compound.
Got it. Okay. Thank you.
So I have a question.
Yes.
Actually, a lot. So when benzene protons are like, when there is a monosubstituted benzene, so when all the proton of benzene are equivalent, and when are they non-equivalent?
Okay. It's very interesting because it turns out that it's all depending on your substituent. If the substituent is not adding electron density or pulling electron density away from the ring, they tend to be equivalent. Okay. If it's monosubstituted, you actually can end up with 3 different peaks if you have any polarity in the bond between the benzene and that group. So even monosubstituted benzene like toluene can have multiple peaks in the benzene.
Yes.
Okay. So it is rare, but every once in a while it'll surprise you and there'll be a single peak with 5 protons. Okay. But most of the time you'll see some kind of splitting, especially in high field NMR. If we were doing 100 megahertz NMR or 60 megahertz NMR, those coupling constants would be very small and would coalesce under 1 peak. But because we're using 300 and 500s now, we almost always see the differences. And that helps us, especially when we have di-substituted or tri-substituted, because now we can look at where the electron withdrawing groups and electron donating groups, and that'll tell us shifts. And so we'll know 2 protons are closer to an electron withdrawing group versus 2 protons are closer to an electron donating group. And we can look at that shift as it moves back and forth.
Okay, so you are saying that the more the polar the substituent is, the more the non-equivalent proton.
Correct.
And one more, there is a chart, the chart D1.
D1?
Yeah, there are only the first 4 substituent, they are showing only 1 peaks. So that's mean all the protons are equivalent?
No, it's showing that those things will shift it in that direction, whether it's ortho, meta, or para substituted.
Okay.
So
okay.
If they're all in the same bracket, you'll only have 1 peak because it's basically showing you where the shift is, not splitting.
Okay.
So this is just showing a shift, not splitting. And then as you go down, if they're separated out, like
yes.
for fluorine, it's M, P, and O. So that means meta is the most shifted downfield, and the ortho is most shifted upfield. And so that's where you look for those based on that. So that's where those shifts are going to be when it's in the meta, para, or ortho position.
Okay.
So some of them are all the same, like a cyano group, they're all the same, and the sulfur is all the same, and the methyl group are all the same, but some of them actually change.
So one more question. Like I was going through this list, there is no amide group as a monosubstitute on the benzene. So have you seen that is there any amide?
Well, it depends. There's the one where the amine is directly bound to the benzene ring. That is like,
okay, yes, yeah.
But if it's the other round, you're looking at it more as a carboxylic acid or a carboxylic acid derivative. So it's going to be closest to the carboxylic acid.
Okay.
So
that was a good one.
Okay. Now one more. Like nitrogen is a quadruple. I can't say it, but it's a quadruple something. So it has a positive charge. Electron can move from the nearby carbonyl and make it positive charge sort of thing. Yeah. So they were saying that if the hydrogen on nitrogen, on that nitrogen are not equivalent because of that quadruple nature of nitrogen. Is it true?
Yeah, and we also see that in IR as well. We see that if you have 1 hydrogen, it's 1 proton, 2
yes.
and 2, so because and you think about it is that they're not just sticking out the same, like they're not 120 degrees apart. They're actually, it's actually sp3 hybridized in space. So they're actually pointing down and toward each other, not like in a trigonal planar. So that if they were trigonal planar, they'd look more equivalent because you would be able to spin it on this axis. Yes. Because it's like this, they are non-equivalent as you spin on that axis.
So they behave like diastereomer protons?
Except they don't split the same way.
Yes.
Because the coupling constant between like two hydrogens on nitrogen, coupling constant is so low, even though they're non-equivalent hydrogens, they're not going to split each other the same way that
yes.
You would see it in the others.
And same goes for if there are methyl group inside instead of hydrogen or nitrogen?
If you have the methyl groups there, they are electronically isolated from each other and they don't split each other.
Yes.
Yes.
Okay.
So I had another question. It was actually regarding one of her previous questions for the chart D1 on just reading it. I just want to make sure that I'm looking at it correctly. But you were saying before about how, for instance, going down, let's just do the OH towards the middle, the alcohol, and it's listed as M, P, and O. And that's how the dot designation is down to the right, correct? So the
Correct.
highest shift amount, the M, would correspond to the, I guess that's 7 point something.
7.05.
Right.
So
And then the para would be higher than that then?
it's the lower. It's that 6.8, 6.9.
There we go. Okay, now I see. Okay.
So
I was having a little trouble reading that, but
yeah. So if you think about it, a metaphenol is going to be, right at 7.05. A paraphenol is going to be around 6.9.
6.9. Okay.
Orthophenol is going to be around 6.75.
And so, okay, so that I guess is my question, was that the variable or the letter M matches up with the first dots. It's not like a inverted,
Yeah,
listing or something.
read it from left to right.
Right.
The letters are left to right. The dots will be left. Read them. The letters correlate to exactly the same order in the table.
Okay.
Like another one, the order of the letters will be shifted in other examples, and you have to still follow whatever that particular functional group has.
I see where my confusion was. It was just the increments on the top. Thank you.
Yeah. So yeah, and they're typically, the numbers are like we see on the spectrum. They run from right to left, and so you just have to follow it. Okay.
So one more question, like how can I know that the nitrogen or oxygen are in the ring, like the part of the ring?
Okay. If we look at D5, you see that if it's like part of an aromatic ring or part of a heterocyclic ring, we're going to see a shift that's different than that if it was outside the ring. So a benzene shift itself is going to be, right around 7 plus or minus, 1. But if it's like inside a ring, it's actually going to be shifted lower. It's going to be a little bit below 7 most of the time. So if you look at the nitrogen-containing heterocycles that are 5-membered rings, they can be above and below depending on and these are the hydrogen shifts. Yeah, so some of them are below 7, and most of them are below 7. And when you have like a nitrogen in a 6-membered ring, that tends to actually put them above 7 because of So for example, the pyridine here, the hydrogen next to the nitrogen and pyridine is almost at 8.6. So you can see these bigger shifts when it's actually part of the aromatic ring as well. And if we go back to table C2, this would be in the aliphatic kind of heterocyclic rings. So you can see that they are a little different as well than the shifts in non-cyclic systems. And remember, when you have cyclic systems, you will start to see peaks coalesce because of symmetry. So for example, in any of these with just the 5 and 6-membered rings, you're only going to see 2 or 3 sets of hydrogens, not a total of 4 sets of hydrogens that you would see in a linear species.
Okay.
So that and IR tends to kind of clear up with symmetry as well, and NMR clears up with symmetry as well. You get a smaller number of peaks with symmetry. So if the spectrum's too simple, but your mass is still high, start thinking rings and symmetrical rings.
Okay.
All right, next question.
So is there a table for like determining the shifts for ortho, meta, and para? Or is it just?
Well, it's other than that D1, not really, because after a while, if you put too many constituents on there, they're starting to influence each other, and so there's no real way. The way you can tell if a benzene ring is multiply substituted or not is you look at the integration. So if you see 5 protons in the integration, then you're looking at mono-substituted. 4 protons, then you look at the shift. How are they? Are they evenly split 2 and 2, or is it 1, 1, 1, and 1? That's telling you something right there. So you're looking for the number of protons that are available. And if you have, 4 protons, but you only have 3 peaks, and it's 1, 1, 2, that's telling you something as well. Okay, that's telling you, you're looking more at probably a meta-substituted, maybe symmetrically meta-substituted, kind of thing. So you don't just rely on shifts there, rely on your integration pattern.
Okay. Thank you.
Is it possible to only have 1 nitrogen if we have an even mass for the mass spec, if we have oxygens in the molecule as well?
If it's a chemical ionization, it will definitely be an even number, because in chemical ionization, it's usually the mass plus 1, the paranion peak plus 1. So if you have an even number in chemical ionization, that could mean you could still have a nitrogen in there. But if you have an odd number in the electron impact, you typically have an odd number of nitrogens. Okay. So you just have to pay attention to that chemical ionization, because but even in chemical ionization, it can be an odd number, because you can have an M plus 18 or an M plus 16 for the methane.
So I just want to make sure, we are going to see the complex splitting when there is an alkene group, when there is an aromatic group, and when there are diastereomer proton. Am I right?
If they are non-equivalent and their coupling constants are significant, you will get a very complex pattern, yes. An example of that is in the homework section.
Yes, that's.
Yeah, as you get toward the end, exercise 3.10A, you can actually start to see really crazy splitting patterns there. And in these crazy splitting patterns, what you're seeing is that they are, 2 different coupling constants for 2 different protons, and they're 2 different coupling constants for 2 different protons, not the same coupling constant for the protons. And that's why we get those splittings.
And in the homework, you gave us the problem number M 3.4. They have very complex splitting, but the number of proton is greater than the peaks. So I just want to make sure that I am on the right path.
I gave you M.
Problem M.
3.4. I gave you 3.2 M. I gave you 3.40.
Oh, no. For grad student.
I didn't give you M.
Okay.
Yeah, the 3.40 is the one.
Oh, sorry. Yes. It's for 3.2. Sorry. Yeah. Thank you so much.
Yeah.
I was.
And this goes back to what Emma was talking about, where look at the splitting in the aromatic range that doesn't fit any pattern we recognize. So we have to start with it. But it's integrated, so each of those peaks is 1 proton. So that tells us that we have 4 protons on our benzene ring. We just have to figure out whether it's ortho, meta, para.
Okay.
And you can see they're shifted way apart. One's down at 7.2 and the other is 0.8. So now that you can start to get an idea of where those might be based on that table with the table D2, not D2. yeah, table D1, you can get an idea of which one's going to be shifted toward one side versus the other, and then still try to figure out how to fit 4 protons on that ring with that shift, making sure they're not in any way equivalent. And you can even calculate coupling constants because they give you the thing in hertz here if you really wanted to.
For the integrations, will we be given them for the NMR spectra? Because I wasn't sure how to read them from the homework.
Okay, well, most of the time what you can do is they'll be given like this. And you just have to say, okay, if pick one of the smallest ones and assume it to be 1 or 2, and then see how it fits all the others. Is it twice as big or 3 times bigger than the smallest one? So for example, in question, let's see, let's do problem 3.4K right here. If you look at 3.4K and we start from left to right, one is about 2/3 the size of the other. So you can estimate that the first one is 2 protons, the second one is 3 protons. That means the one down at 4 ppm looks like 2 protons, and the one down at 1.5 looks like 3 protons. Okay, and so you can estimate from that. You know, the exact number is not, you know, as critical as the relative ratio. And so from here, that would give us, oh, you know, we have 5 protons on the benzene ring and then 5 protons somewhere else. Okay, so you don't have to know the exact number, but that relative ratio is where you get the information from. Okay. Yeah, and I'll post the homework tomorrow morning, the key to the homework, so that you'll have that to check your answers on that. All I have to do is finish up one problem, but I have them all done other than that. And did I post the homework for number 1 and 2 yet? No? Okay, I'll post that too. 1 and 2. I did.
So about that exam, so like previously you told us that for mass spec we need fragment pattern and parent peak and hydrogen diffusion index. And for the IR you have to told that you have to show these things like where are the functional group. What about the NMR?
Okay, for the NMR, because what the NMR is going to tell us is the absolute structure. The absolute structure will be that, and so you'll have to label your structure as, you know, peak A, peak B, peak C. So I'll give an example of what I want as far as the results are. And so you're still going to do your final empirical formula. You're going to do the hydrogen deficiency index and the structure, and then you have to put on the NMR spectrum that this is peak A, this is peak B, this is peak C, and it, you know, the number of protons will be you know, obvious from that.
Okay. About the chemical shift, do you want the particular, like the way that is written in the book, that this proton show the chemical shift of 2.9? Do you want this, or the range is fine for you, that this range is coming between 4 and 5? It's mean this thing is possible, sort of thing.
Yeah. Well, on the Proton NMR, because you're comparing not only shift, but you're comparing integration and splitting, just by assigning the peak to that particular part of the compound is enough, okay? Because you have to compare those 3 things to actually assign that peak. And so just by assigning the peak to that part of the structure is enough for me.
Okay.
Okay. So, you know, you might say,
like there is a question in homework that calculate the chemical shift of each proton. So that was making me a little like, how can I do in exam?
oh, okay. Well, that is number 1 to get you practiced at doing it and looking at where things might be, it gets you to use all the different tables. Notice in the instructions it says, and show where you got it, right?
Yeah, that's the hard part.
Right. Sometimes you're going to use the table, you know, sometimes you can easily show it in just in table A, appendix
Yeah.
A1 or A2, but sometimes you have to use appendix B because it has two different things on it. Sometimes you can draw attention to say, oh, look at D2. D2 has a structure that's very similar to this. I can get 3 of the peaks just out of D2 and then have to go calculate the last 2. Okay, so the activity was designed to get you to use all the different tables and use them, you know, in different ways. Okay. So, oh, I have my thumbs up. You can't see that. So.
Okay, and in previous activity there was only peak, not the splitting. So there will be available next exam because it was very difficult in activity. It will be easy if splitting is also available.
So like having the
splitting pattern of each peak.
Okay. Oh, saying whether it was doublet, triplet, or whatever.
Yeah.
Okay.
Yeah.
Yeah. Most of the time, I when they were hard like that, I tried to have it split out, or you know, focused in on those particular peaks so you could see. But on the homework, yeah, you can't zoom in. But on the exam, you should be able to, because it'll be on, or it'll be on your computer. But if there's any ambiguity, I'll make sure to mark it as, you know, doublet, triplet, or whatever.
Okay.
Fluorine isn't listed on D1. That is true. It's not. It's approximately the same as chlorine.
Yeah.
But it is not on the table. You are correct.
So like on the first exam, you had like a thing of a list, I guess, of things that you would do to give a partial credit. Is that how?
Uh-huh.
Yeah. So what would be the things for this test?
Okay, for
Like
this,
the same things.
I have like on the last test, I'm have boxes where, you know, anything in the box, the more you fill out, the better. And so, for example, things like final empirical formula, final hydrogen deficiency, and remember, you got to recalculate the hydrogen efficiency every time you do a substitution. And then the final structure, and then where assigning the different peaks in the NMR to the final structure. And you can use A, B, C, D, you can use 1, 2, 3, 4. It doesn't matter, just as long as the structure you draw has something on it that shows me where the peak is in the proton NMR.
Okay.
And then when we start doing carbon NMR, we're going to do the exact same thing. You have to assign all the carbons. So you'll have C1, C2, C3, C4, and then, you know, HA, HB, HC, HD, you know, and so that you can assign them all separately. So we know all where everything is. Okay. Because as we get more and more information, we have to be more and more precise about the answer. And also in the mass spec, if you have like major fragments, like, oh, this is the CH3CO peak that always comes off, or this is a tryptolium, or this is a benzene, assign those. And so even if you know, end up with the wrong structure, you'll get credit for those. See, that's why it'd be difficult to have it just on Canvas as a quiz, because if you just have one chance to make the answer, that was yes or no. And this gives you an opportunity, you know, this was my thought process, and it's like, oh, well, this was where you kind of went astray. So, but all of this stuff makes sense. And so you get partial credit for the stuff that made sense.
Yeah, we really appreciate what you are like. It's everything is very good.
Well, thank you. So
yes, appreciate it. Thank you.
Again, this is to have you use it as a problem-solving thing, So as you go off and do great things in the world, you'll go back and you'll have this book on your desk and it's like, well, did I get it or not? Is this right or not? You know, so, and then you'll just use this skill for the rest of your career. I actually had to do some really hard, down and dirty coupling constant equations when I was doing multiple nitrogen experiments. We had high nitrogen compounds when I did explosives. And it was very difficult because there no NMR on any of these except from back in the 50s, and they were all 50 megahertz NMRs. And they were all single peaks, and I had multiple peaks. And so I had to figure out what the coupling constants were and everything like that to assign these peaks. The crystal structure really helped too, but we also got crystal structure, but it was hard to identify by NMR at first. And let's see, approximately. Yeah, chlorine is approximately equal to chlorine on that table. The problem is that it's so electron negative. It's a more electron negative, but chlorine has the ability to hyperconjugate, donate back a little bit. So it's a little different, but it's a good starting point. And then you'll see the fluorine in the mass spec and stuff anyway, if you have fluorine. I think we had oh, yeah. Yeah, we did actually have fluorine, didn't we? That's right. But so when we get to fluorine NMR, actually there's some really cool shift stuff in fluorine NMR as well. And we'll take a look at that. Okay. Well, that's all I have really for you. And so if you have questions, you can stay and ask questions. If not, I can just go off and finish my keys for the homework so that you'll have that as a study aid as well. All right, well, I'm going to stop recording and just let you ask questions until you're bored.